Hello students, let's get started with a new chapter, that is Central Processing Unit, and it is the first part of this chapter. Okay, and your topic is now stack organization. And I'll explain now about register stack. I'm not going to explain more about stack because you are studying in data structure. In short, it is a LIFO, last in first out type of data structure, and its insertion operation is known as push, and the deletion operation is known as pop, right? To know more about register stack, we will consider a 64-word stack. Okay. It is a 64-word stack, so the addresses will be numbered from 0, 1, 2 up to 63, right? Okay, now tell me, if the size of the stack is 64, then what is the address size? That means by how much bits I will be representing these addresses. You know already, 64 equal to 2 to the power 6. That means address size will be 6 bits, right? That means this 0 will be represented by 6 zeros, 1 will be represented by 0, 0, 0, 0, 0, 1, 2 as 0, 0, 0, 0, 1, 0, and so on, and 63 as 1, 1, 1, 1, 1, 1, right? Clear? Now we will consider 4 registers which are associated with this stack. One is data register. Okay, I'll explain the function of this. One is stack pointer. One is full, another is empty. Okay. Now what is DR, that is data register? You already know that whenever I talk about a memory, one data register and one address register are always associated to that memory. Here that data register is DR and address register is stack pointer. Okay. Now what is the function of data register? See, you know that in case of stack, whenever we want to push a new data item into it, we have to push it onto the top of the stack. Okay, and whenever we want to pop something, that is whenever we want to delete a data item, that is also from the top of the stack. Whatever be the data, it is performed through this data register, right? If I want to push a new data item, that is kept into this data register first, then from data register to the top of the stack. Likewise, whenever we want to delete or we want to pop the top of the element, top of the stack, then it is kept from top of the stack to this data register. Clear up to this, the function of data register? Now what is the function of stack pointer? You know that stack pointer is working as the address holder. We know that stack pointer holds the address, right? Now address of what? Stack pointer holds the address of the top of the element. Okay, now suppose A, B, C, these are the data kept in the stack. Okay, so top of the stack element is C. Now stack pointer will be holding the top of the stack element's address, that is 2. 2 means this 0 0 0 0 1 0, this is kept in stack pointer. Clear up to this? Okay. Now what is full and what is empty? These are nothing but flag register. These are 1-bit registers. Okay. Full means when the stack is filled up with data. That is, if the stack is full, this full register is set to 1. Okay. When full is set to 1, that means the stack is filled up. And when the stack is empty, there is no data in the stack, then empty is set to 1. Clear up to this? Now we have to define push operation and pop operation using register transfer language. Okay. Now if we want to push a new data item, what will be our first responsibility to do? See, the new data item is now waiting at data register. It has to be kept or it has to be pushed at the top of the stack, right? But stack, we know that stack pointer holds the address of the top of the stack, right? So when we want to push the new data item from data register to the top of the stack, first of all, this stack pointer needs to be changed. Changed means it has to be incremented since it is in increasing order, right? So first of all, we have to make it, first we have to increment it. Stack pointer is incremented by 1. For example, suppose stack pointer is now pointing at C for the time being, at 2, address 2. So if we want to push new data item from data register to stack, the new address will be 3, top of the stack will be 3. So first of all, we have to make it 3. After that, we will push it from data register to stack. So source is there, source is data register and destination is aim of SP. Clear up to this? After pushing data elements into the stack, what is the way to understand whether the stack is full or not? There must be one condition to be set, right? In this example, we consider it as a 64-word stack. So initially, the stack pointer will be pointing to 0. Okay. That means initially stack pointer is pointing to 0 and empty is set to 1, right? Initially, stack pointer points to 0. That means empty is set to 1, right? Now in this example, the highest address is 63, right? 63 in binary it is 111111. Okay. Now after pushing at 63, if we increment the stack pointer by 1, what is it? 110, carry 110, carry 110, carry 110, carry 110, carry 110, carry 1, right? If since we are performing a 2's complement addition, so 1 is discarded. It is basically 0 0 0 0 0 0. That means 0 address. Okay. To push new data item, when we see that after incrementing this stack pointer by 1, this stack pointer is pointing to 0. That means the stack is full. Got my point? So let's write it. If stack pointer equal to 0, then full is 1 and empty is 0. I repeat this thing. To push a new data item, our first step is to increase the stack pointer by 1, because the new data item is waiting at data register and the stack pointer is pointing the top of the stack's address. Now to push new data item, we have to increment it since the addresses are in increasing order, right? That is why stack pointer is incremented by 1. After that, the data item from data register is set at m of sp. Now we have to check whether the stack will overflow or not. To push new data item, we have to check after incrementing this stack pointer by 1 whether it is pointing to 0 or not. Why 0? Because in this example we are considering 63 as the highest address. 63 in binary is 111 111. If we increment it by 1, plus 1 means 0 0 0 0 0 0 1. Since it is a 2's complement operation, so we discard this carry. Remaining bits are 0 0 0 0 0 0. That means 0, the decimal 0, right? So we set it as a condition to be full. That is why if SP is 0, then full is set to 1 and empty is 0. Got it? Now let's come to pop operation. To pop or to delete the data item from the top of the stack, the top of the stack element will be kept from top of the stack to data register first. Then the stack pointer will be decremented by 1. Let's write it. From top of the stack, m of sp, because stack pointer is pointing at the top of the stack, right? From there to where? To data register. Now the next step is to decrement the stack pointer by 1. sp is sp minus 1. Now we have to check the underflow condition, that is whether the stack is empty or not. How? In this example, 0 is the lowest address from where the data can be popped last, right? So after popping from 0, if we perform this stack pointer is decremented by 1, decrement operation, that means 0 minus 1. 0 is the lowest address from where we have popped data. Okay, for underflow condition I'm considering. Let's perform it in binary. Okay, 0 0 0 0 0 0 1 means 0 0 0 0 0 1. Make its 2's complement 1 1 1 1 1 1. Now add these two, 1 1 1 1 1 1. This is equal to 63, right? That means if we try to delete when the stack is empty, if we then also try to delete or try to pop data, then the stack pointer will be pointing to this. Okay, so it is our condition. If stack pointer is equal to 0, then actually we shouldn't try to delete, that is we shouldn't try to pop data when stack pointer points to 0. Then it will underflow condition occurs, right? Then empty is 1 and full is 0. Got it? Done.